Good morning, everybody, and thanks for coming. I just want to start by congratulating the Leaf crowd, the organisers, for having put on such an amazing event. It's extremely humbling to me, having been in this movement for so long, and having had to spend so many years taking so many bullets when this idea was so much more heretical. It's very wonderful to see how legitimate it's become. We've even got to the stage where people are forgetting what SENS stands for. That's really good news. One thing I've been pointing to over the past few months is that the word rejuvenation has started to be used by actual, normal credentialed mainstream gerontologists to mean what it actually means, actually turning back the biological clock. The connotations of cosmetics and so on has now actually finally been forgotten. It's now 15 years since I named my journal Rejuvenation Research, and I had to fight repeatedly to keep that name for the journal because it was felt to be threatening the sales of the journal, but that's not happening anymore. So that's pretty good news as well. But for people to be able to put on a conference like this with such a stellar set of mainstream gerontologists as among the speakers is really an enormous sign of where this movement has come to. And so I totally want to congratulate everyone who's involved. And to be honest, I'm beginning to see the light at the end of the tunnel where I can just retreat into glorious obscurity and spend my life doing maths in my hot tub. But not yet. So today I'm going to try, as I always do with audiences that are largely familiar with SENS's work, I'm going to try and talk about something a bit different. I'm just going to give a very brief background to what SENS is all about and the paradigm that we pursue at the Foundation, because I know that there's probably nobody in this room that that's unaware of it. So the essence of what we do is all founded on a concept that I first started to promote and to propound almost 20 years ago now, namely that the most practical and most feasible way to keep people healthy late in life was to repair the various types of lifelong accumulating damage in the body that eventually exceed what the body is set up to tolerate and drive the emergence and progression of late life pathologies. And this was in sharp contrast to either the traditional geriatric medicine approach of attacking the pathologies rather as if they were infections. Have I got a pointer on this, I wonder? Yes, I probably do. Yeah, there we go. And also in marked contrast to the traditional gerontologist approach of trying to essentially make the body run more cleanly and generate damage more slowly than it normally would. Since it was such a paradigm shift, it did, of course, take a number of years to be really properly understood. But all I was really saying was that we need to just remember what aging really is. It's not some bizarre, poorly understood, emergent phenomenon of biology like, consciousness. It's just the same thing at root as aging of an inanimate machine like a car. And therefore, the comprehensive preventative maintenance approach is something that should, in principle, work just as well in a living organism, like such as you and me, as it does successfully in inanimate machines, allowing us to have cars that are 100 years old and so on. So then, of course, in order to make this concept fly and to show that it was not just a common sense approach, but actually a practical one had to actually describe what this damage actually is and to describe various proposals for how to actually implement this repair. And, of course, that's what SENS started out as, this kind of 7-point subdivision, classification of the damage of aging on the left-hand side with the corresponding generic therapies on the right. And of course, the good news is that this classification has very much stood the test of time. And no category number 8 has emerged. It's kind of not surprising because even when I first started talking about this nearly 20 years ago, all of these things on the left were already well-established phenomena that were very much foci of study by gerontologists and had been for at least 15 or 18 years before then, in many cases a lot longer than that. So this is it's circumstantial but still very strong support for the plausibility of this approach that this model has been able to survive for a couple of decades now without significant alteration. And of course, as we all know, and as in fact Oliver and Keith have just referred to, we've now got the whole thing being reinvented, by various people in slightly different forms, essentially exactly the same idea becoming very much more acknowledged as legitimate and mainstream and orthodox, and in fact perhaps as the most practical way to go about actually addressing the health problems of old age. But what I want to talk about today is how hard this really is. Because as I already, mentioned here, there is this question at the bottom. The body, of course, is far more complex than any man-made machine. And for that reason, we have to address the concern that the implementation of a damage repair approach may also be impractically complex. I always emphasize how ridiculously complex our metabolism is, which is really what has thwarted the attempts of gerontologists to slow down the rate at which damage is created in the first place. And I also emphasize how complicated the pathologies of aging are, the fact that so many things go wrong with us late in life, and they go wrong at more or less the same time, which means they exacerbate each other. It's really pretty nasty. And so a kind of natural assumption would be that this complexity would also be true of the thing in the middle, the damage. And if that were true, then yes, the damage repair approach would be the common sense approach, but it still wouldn't be practical. So classifying it in this way with 7 types of damage is a start. It says, well, okay, this is a manageable number of categories, but maybe that's not a sufficient argument. Maybe we need to dig deeper into this. And about 5 or 6 years ago, I was in Russia, where I'm actually going tomorrow. Again, I love going to Russia because they're sensible people over there. They don't have this pro-aging trance. I was in Russia, and I had a glorious conversation over dinner with the Harvard professor Vadim Gladyshev, who I think is also speaking here. I'm not sure if he's already here. Vadim was much more pessimistic than me with regard to this complexity issue. It was clear that he and I thought very similarly about the nature of aging and how we ought to think about aging, but he basically felt that, no, we're not going to really be able to implement this damage repair approach. And, dinner is not the world's best format in which to have a comprehensive conversation, and sure enough, we didn't really get very far, and we had to kind of leave this thing. But a few years later, I was running a conference this past March, courtesy of Michael Grieve, who I just saw earlier on. And one of the things I decided to do was to continue this conversation, because Vadim had agreed to come and speak at the meeting. And so what we did was, we had a debate on stage, and we got considerably further along the trajectory of this question of whether the comprehensive damage repair approach really is practical. But I wouldn't go so far as to say that we actually resolved it. I guess that's not surprising. So I've been thinking about it more, and I think it's a very, very legitimate question to be thinking about, for all of us to be thinking about. So I thought that's what I'd do today. And I will tell you up front that I'm not going to come to any conclusions today. I'm going simply to address some of the points that I think bear on this question, and perhaps in ways that some of you may have overlooked in terms of why these things matter or whether they actually help to resolve the question. So essentially, this is what I'm going to talk about. I'm going to give a couple of the main reasons for pessimism, the main things that Vadim correctly pointed out as potential challenges, and then I'm going to give a bunch of reasons why the challenges may not be as great as they initially seem. So let's start here. I've got these 7 categories, but I certainly do not think that there are only 7 types of damage at all. the reason why the hallmarks of aging paper decided there were 9 categories, and Brown and Kennedy's Pillars of Aging Paper, I think they had 6, and David Sinclair has 8. The reason why is because it's pretty arbitrary, in some ways at least, how to subdivide the list of types of damage. There are lots and lots and lots of them. And really the merit of classifying them at all is simply that we can then classify the types of therapy. That each category has a kind of generic approach to fixing it, and I'll come back to that shortly. But the point is, we are discovering new types of damage all the time. The only reason why the 7-point classification that I've been talking about for so long is indeed standing the test of time is because so far it has been easy and natural to fit the new ones into the existing categories. A great example would be systemic cardiac amyloidosis. This is a condition that affects the elderly. It especially affects the very elderly. It was discovered only relatively recently, certainly well after I had first started propounding SENS, that that this particular type of amyloidosis is the #1 killer of supercentenarians. And prior to that, this amyloidosis had been known about, but it had almost exclusively been studied as an inherited, early onset problem caused by mutations that make the relevant protein, transthyretin, more amyloidogenic than it naturally is. So that was, a completely new problem in aging that people had really not thought of before, or certainly not addressed. And luckily, you might say, it didn't need a new category because we already had the amyloid from Alzheimer's as a problem that one needed to address using the immune system. And of course, it was very promising work was already coming out, which indeed was part of what led to SENS in the first place. The first paper that really made the breakthrough there came out in 1999. But yeah, so basically the same approach was likely to work. And sure enough, in due course, we funded a group in Texas to work on exactly this, to work on immunotherapy against transthyretin amyloid. And that group were very successful. They published some very nice papers, and they made enough progress that they were able to spin out that work as a private company. I think I saw Richard Massey in the audience earlier. That's another success story. But here, the point is here that we are discovering new types of damage all the time, and so it's reasonable to be cautious about whether we will at some point discover ones that do not naturally fit into the existing classification. Another thing that Vadim pointed out, and again he's completely right, is that we are beset with the problem that all types of damage become pathogenic at roughly the same age. And of course we understand from an evolutionary perspective why that is, because it's essentially a selection thing, that the process of creation of damage is a multi-step process where there are intermediates that form that can be repaired but sometimes aren't. So essentially the types of damage that accumulate are ones that somehow escape from the repair processes of these intermediates that here I'm calling pre-damage. And of course, the repair is genetically coded. We have actual genes, actual enzymes that do that. So those genes have to be maintained through natural selection. And if, for whatever reason, we were to have a genetic pathway for the repair of some particular type of pre-damage that was unnecessarily good, in other words, that prevented the pre-damage from becoming actual damage until, let's say, we were twice as old as for other types of pre-damage, then the genes for that repair pathway would accumulate mild loss-of-function mutations that would increase the rate at which that damage accumulates until everything kind of leveled out. And so that's what we see. Now, there is an exception to that I'll come to later on, but that is the general principle. And what it means, of course, is that if we fix a lot of types of damage, but not all, then the prediction is we're pretty much going to get sick and die on schedule anyway, because of the things that we haven't fixed. But luckily, there are some counter-arguments to all of this, and I'm going to go through all of those now. First one, the classification thing. So I mentioned earlier that the basis for this classification... Oh, here's that in. Jolly good. Were you here at the beginning? I know. The basis for this classification is to organize our thoughts and our design around the nature of repair. In other words, we identified generic repair therapies which can be applied to all of the examples of damage that exist within a particular category. And the utility of the classification comes entirely from that. There's obviously, if you've got 1,000 things, you can put them into 7 boxes in a lot of different ways, and the only reason that's useful is because of the therapies. So then, why is that useful? Well, it's basically because we can reuse what we've already discovered. If you've got a therapy like, for example, immune therapy against Alzheimer's amyloid, and it works, and incidentally, for those of you who don't know, we are at that point now. There are at least 4 immunotherapies against Alzheimer's amyloid that definitively, in human beings, actually remove amyloid from the brain of Alzheimer's patients. Of course, those therapies do not, on their own, confer appreciable cognitive benefit because, no surprise, I mean, I'm not surprised by that because, of course, there are lots of other things that go wrong in Alzheimer's disease, which are not addressed by that therapy. But the point is we have that. Now, as I mentioned just now, immunotherapies for other amyloids should be pretty easy to develop, and we can reuse what we have learned about what works and what doesn't work in Alzheimer's, and thereby speed up the process of inventing the next immunotherapy for the next amyloid. And the more times we do that in a given category, the easier it's going to get. So I think that's very important to take into account when we try to quantify the time frame that is likely to exist for actually succeeding in developing a sufficiently comprehensive range of therapies against the types of damage in aging. Then I said I was going to talk about an exception to the business of everything becoming pathogenic at more or less the same age. And that comes down to a concept that I coined this rather unpronounceable name for, protagonistic pleiotropy. So many of you here will know what antagonistic pleiotropy is. It's the idea that first put forward in 1957 by George Williams that we may have genetic pathways in the body that are actively bad for us late in life simply because they are good for us early in life and there has been insufficient selection to turn them off, essentially, late in life. And so we end up actually, having things that are genuinely killing us. Now, the concept of protagonistic pleiotropy is kind of the same thing turned on its head. Here we have a pathway that's good for us early in life, and it would be good for us late in life because it repairs or it prevents the accumulation or it slows down the accumulation of some particular type of damage. But in this case, what we propose is that there are 2 types of damage that are both prevented by the same genetic pathway, and one of them accumulates much more slowly than the other. In other words, that genetic pathway is being selected for on the basis of the type of damage that accumulates fast. That's what determines its selected quality. But then it's repairing the other type of damage unnecessarily well. And I described this concept in the context of cancer. I basically said, well, cancer is really bad for us even if one cell goes badly wrong in the wrong way. Therefore, it is going to be the principal driver of the quality of our DNA repair and maintenance machinery. And that means that the rest of our DNA is going to be the stuff that, mutations and epimutations that don't have to do with the cell cycle are going to be maintained and prevented unnecessarily well. So we don't need to worry about them in the context of keeping people healthy for a lot longer than we can currently do, than they naturally do. And the concept applies elsewhere as well. It applies, for example, in relation to glycation, non-enzymatic glycosylation of the extracellular matrix. Because here we have a rather baroque tree of chemical reactions that happen following the initial reaction of a circulating sugar molecule with a lysine or an arginine on an ECM protein. And some of those reactions probably matter a lot in aging, in particular the ones that cause crosslinks and reduce the elasticity of tissues like the major arteries. But other ones probably don't. Adducts, in particular, that simply just change the amino acid, but it wasn't like an amino acid in an active site of an enzyme or anything like that. These are probably just harmless, and they accumulate, but they accumulate really slowly because the pathways that make them not accumulate any faster are the same pathways that are also limiting the rate of accumulation of the crosslinks. So, that's actually an important thing to take into account, and it reduces the number of things that we actually have to go after as damage that we need to fix in order to keep us healthy for longer. Finally, there are some types of damage. I can actually only think of one that I'm sure of, which really just doesn't need any pathway at all. It's just too slow to matter. And the one I'm thinking of is amino acid racemization, the alteration of an amino acid into its mirror image form. This happens especially for aspartic acid, but it happens really, really slowly, even in proteins like the extracellular matrix that are not turned over at all. And nobody's been able to make a good case that the extent of this actually has any pathogenic consequences whatsoever. Next one. Okay, so I'm not sure whether I like this name. I've been calling it the penumbra effect for a long time, but maybe I should think of a better name. The concept here is, as I mentioned already, that damage is laid down by multi-step processes that have intermediates. The thing is, though, when we measure the amount of damage in a tissue by amount of a particular type of damage that we measure in some particular way, generally what we're measuring is not just the final end product. We also tend to measure these intermediates. For example, lipofuscin, the fluorescent pigmented stuff that accumulates in the lysosomes of non-dividing cells. First of all, we don't actually know whether that stuff is particularly causative in aging, but it very well may be, and we'd like to get rid of it. But here's the thing. What we see is a very heterogeneous range of different molecular species. And some of those molecular species may be genuinely incapable of being broken down by any enzyme that we naturally have, with the result that in order to get rid of it, we would need to introduce new enzymes, and as many of you know, that there's a lot of work that we've done over the years along those lines. But there's also going to be a bunch of stuff that is actually capable of being repaired, that's kind of on the pathway towards this completely immutable stuff, and it's just repaired rather slowly, and perhaps increasingly slowly as a result of the impairment of other things that's going wrong at the same time. So there, we have to remember that if we were to fix all of the truly end-stage irreparable damage, then we would also be essentially re-empowering pre-damage repair mechanisms so that they could get a better handle again on this pre-damage and automatically, spontaneously diminish its abundance. And so, this is again something that may substantially lower the complexity of what we actually have to do relative to what it seems at first sight that we have to do. Another thing that I think is also worth mentioning, because I don't mention this enough, is that the incapacity of traditional geriatric medicine to successfully keep people healthy late in life is something that we may actually be able to change by introducing this damage repair. When I talk about this, normally I talk about these as alternatives, and I talk about geriatric medicine as a failed approach to the health problems of late life. But the fundamental reason, the most important reason why it's a failed approach is actually not the complexity of the pathologies of late life. Rather, it is the fact that these pathologies are being driven by something that's accumulating, namely this damage, the lifelong accumulating damage that's initially asymptomatic. And the idea, of course, of maintenance, of damage repair, is that the damage will not be accumulating anymore, which means that geriatric medicine that currently doesn't work will actually work a lot better than it currently does without any actual improvements to the actual underlying therapies. So again, this is something that may limit the how hard it is to implement this approach in a manner that actually works. Another thing I really want to mention, which has come to the fore a great deal over the past couple of years in relation to senolytics, is that the types of damage that accumulate do have a certain amount of crosstalk between each other, and this crosstalk, the magnitude of it, is considerably greater than anyone, I think, certainly I, would have predicted even 5 years ago. You know, you can look at each of the damage categories and you can say, well, okay, you know, atherosclerosis ultimately arises from molecular waste products inside the cell, and Parkinson's disease ultimately arises from cell loss, and so on. And this is not 100% true, but it's broadly true that most of the pathologies of late life are ultimately the result mostly of one particular category. So then one might say, well, okay, that's a bit of a shame, because it means that if we want to actually keep people healthy and stop them getting any of the late life pathologies, then we've got to get stuck in everywhere, because if we fix 5 or 6 of the types of damage, then the last one that we haven't made any progress on is going to kill us more or less on schedule regardless. Now, I always knew that there was some crosstalk, and I made a particular case even 20 years ago in my thesis, that mitochondrial mutations might well be an example of a type of damage that had a very far-reaching crosstalk, a far-reaching knock-on effect on things, simply because of the mechanism whereby mitochondrial mutations are important at all, which, again, is still controversial, but I believe that it's highly systemic. But for everything else, I thought, well, probably no. But then Unity came along, well, the Mayo Clinic, of course, in collaboration with Judy Campisi at the Buck, and they started to show that if you eliminated senescent cells from mice, then they got better in ways that you just wouldn't have predicted from that, ways that seemed to be completely independent of senescent cells. And of course, work has gone on since then, and Unity have done more and more work on normal mice, not progeric mice, and there's also been, a lot more work on different ways, on different ways to go about all of this. So, this is good news. An additional feature, which is the last thing I'm really going to say here about this crosstalk, is that there's also crosstalk at the level of the technologies. For example, many of the SENS strands, in order to achieve them, are going to need considerably more powerful, more effective, and safer, for that matter, gene therapy, somatic gene therapy, than what we have today. And, we've been working on that for a long time, but the point is, the closer we get to really good gene therapy, the easier many of the SENS strands are going to get all at the same time as a result of the same technology. So that's another kind of crosstalk. So I told you at the beginning I wasn't going to come to any conclusions, and I have kept that promise. But the fact is that I hope I've given you a lot of food for thought. There's definitely no clear answer to the question, how long is it going to take to implement the whole panel of damage repair well enough to achieve longevity escape velocity? Definitely no answer. And one could say, well, who cares anyway? We're going to just do it as fast as we can, and it doesn't really matter. But something that Vadim pointed out in the debate in Berlin was that if we decide that it really is, just too hard, then it doesn't mean we abandon it, but it does mean that we have a basis for prioritizing other types of approach that may be more at the level of slowing down the creation of damage and so on. And I kind of buy that. I think that's true. So I think we do absolutely need to put more effort into quantifying the true required complexity of the damage repair paradigm. And that's all I want to say. Thank you.